So let's recap. The two alternative hypotheses are positive autocorrelation and negative autocorrelation. Positive autocorrelation is, and we've been through this before, clustering. Like values tend to be in like locations, in similar locations. Or the other way to put it is that neighbors are similar. And this is the way we will actually quantify it, because we will compare in a statistical way the value at a location with some summary, some average of the value at the neighboring locations. And that will turn out to be our statistic. That will turn out to be the way that we quantify this. Now let me take a minute to discuss the substantive reason behind these patterns. And this is very similar to what we said when we talked about point patterns. And in fact, in a few minutes, we'll get a similar slide about true contagion and apparent contagion. Remember, in a point pattern analysis, once we identified that clustering was going on, so there was a grouping of the points more so than would be the case randomly, there was really no way for us to conclude how that clustering came about. What is the process that gives that clustering? And I think, as you've seen in the first assignment, when you use a process to generate a cluster pattern, it sometimes doesn't look quite the way you would expect it to look. And even though you simulate it with a clustered process, some of the patterns that you ended up with didn't seem that clustered. They seemed actually random. And the other way around too, when you simulated dispersed patterns, they sometimes were basically random. And that's the tricky part. How do we flip this around and go from the observations of the cluster to figuring out what is the process that gave us this cluster? Now, in the case of discrete spatial data, of lattice data, we are concerned with the values. What is the model that yielded the particular pattern of these values? And one natural instinctive interpretation is to say, well, we get these clusters because of diffusion, which is another word for contagion. So we have, like in medical geography or criminology, we find clustering of crime rates, of high crime rates, or clustering of high cancer rates, okay? Or clustering of high influenza rates, bird flu, okay? Which is contagious, right? Cancer is not. So is this high rate of bird flu because of some element was introduced that had the disease and spread it around? Or is it because that particular location is somehow more amenable to getting the flu than another location? And our natural instinct is to conclude contagion when we see clusters, but it doesn't have to be. And it's very important to distinguish this. The direction of causality does not go both ways. If you have diffusion, you end up with clustering. But if you have clustering, that doesn't mean it is because of diffusion. It could be because of other things, as we'll see in a few minutes. So this is very important. A lot of people, and even in papers that I referee, fall into this trap, in that they find spatial autocorrelation and interpret it. When you write up the conclusion, the words part, you say, well, there's diffusion. Well, not necessarily. Okay. And in order to be able to say this, you really need additional information. Typically, the additional information comes from the time dimension. Once you have observations at multiple points in time, you can see whether there's a dynamic process of contagion going on or of diffusion going on, which would show itself in a changing of the cluster, whereas if it is a structural difference, then the cluster would always be in the same place. because the structure doesn't change. Okay? So you need, the bottom line is you need additional information. So just to give you a concrete, if you can call this concrete, a better feel for what it looks like, this is the same idea. We start with Z here, which is just standard, normal, random variable, randomly allocated over the grid. And we move on and up the spatial autoregressive coefficient, 0.5, 0.7, and 0.9. Now, the difference between these two is not that great, I mean, visually. Okay? So it becomes very difficult to distinguish between the two. And what we'll see is that a statistical test will, without any doubt, reject the null hypothesis here. It will say, no way is this spatially random. But for us, it's going to be very difficult to do this by eye. So one of the lessons of this course is, if you remember, only one thing is don't trust your eyes. Okay? It's very misleading. And don't ever say, I see a cluster here. Okay? You will have enough tools by the end of the semester to be able to assess that and to be able to say, there is a probability of this much that this is in fact not random and is a cluster. And that's the way to go about it. Because as you see, at least for me, it's very difficult to start drawing the line visually and saying, well, yeah, sure, this is a little extreme here. But between these two, and especially between these two, I can't do it. But our test statistics will be able to quantify, in a sense, the degree of non-randomness that we have here. And that's what it's all about. Okay, negative spatial autocorrelation is a little more difficult concept. I like to refer to it as the opposite of clustering, which doesn't help. It's really a checkerboard pattern. It's the dissimilarity. So it's compatible with the notion of competition. But then, again, you know, don't fall in the same trap. Competition is just a natural way to think about the interaction that goes on. So, you know, if you think of market areas, for example, and stores, the distribution of stores, small grocery stores, they tend to spread themselves around in the city. They're not all next to each other because they each have their little market area of people who like to walk to the store. And so if they move themselves further away, they maximize their market area rather than all moving in the same spot. So that is non-random. That is some structure that we could associate with a behavioral process. But we don't know what the behavioral process is just from assessing that there is negative spatial autocorrelation. So it's the same thing as with the contagion. We really have to be very careful before we draw conclusions. So one way of saying what negative spatial autocorrelation is that neighbors are more dissimilar than they would be under spatial randomness. So finding a high value next to low values is unlikely relative to spatial randomness. Or finding a low value next to high values is unlikely relative to spatial randomness. And the same problem here. Again, we start with completely standard normal random variates in the upper left corner, and then we go to negative 0.5, negative 0.7, negative 0.9. Now, at which point does it become more checkerboardy? I really can't tell. As far as I'm concerned, they all look a little checkerboardy, but you know, it's not true. This is totally random. This is 0.5 is very high, as we'll see later. You know, in a lot of applications, you don't get 0.5. You get 0.2, 0.3, and that's already highly significant. So 0.5 is extremely significant, but to the eye, it's very difficult to distinguish it from true spatial randomness, and that's why the techniques are there. So let me just reiterate, because I see it too often. Don't go both ways. You know, the fact that you find clustering could be that there is a diffusion process, but not necessarily. The other way is more natural. Diffusion will give you clustered outcomes. But when you find a cluster, it could be due to structural factors without any contagion whatsoever. The same example I gave earlier on, you find a village where everybody's sick, cross-section, one snapshot, one picture. Right? Are they sick because somebody came in and made them all sick? Contagion. Or are they sick because the water is bad and they all drank the water? Structural factor. Okay. Crime, you see high crime in a neighborhood. Is it because a new gang moved in and started stirring things up? Or is it because the neighborhood is poor, broken windows, abandoned houses? Structural. Okay. Without that extra information, you cannot draw these conclusions. But what you can say is that the fact that you observe this particular pattern is not compatible with randomness. So there is a structure there. And just to say it one more time, this is the distinction between true and apparent contagion. We really cannot, from a cross-sectional observation, draw conclusions about the causal factors behind the pattern, behind the clustering. And true contagion is a true dynamic contagious process, which, whenever I say dynamic, means time is involved. So we need observations in both space and time. Or it's apparent contagion, which is more, we haven't really talked about this a lot in this class, has more to do with spatial heterogeneity. Things are not the same everywhere. Space is a way of structuring reality so that things are high in one particular subarea and low in another for particular reasons. If you look at house prices in cities, they tend not to be random. The prices are higher in certain neighborhoods than in other neighborhoods. Why is that? That has nothing to do with contagion, maybe speculative contagion, but it has to do with structural differences, with the stratification you find in certain cities. Interestingly enough, this is not a uniform phenomenon. You find this in US cities. You do not find it necessarily in cities outside the US. We have a very interesting example of house prices in 3 major cities in India, and there's very little spatial autocorrelation there. There is stratification, but it's different. In the US, you could pretty much tell by where one lives what kind of income category or socioeconomic status one has, because it's so stratified. And in some places more than others. I think I may have told you the story about Texas. In these North Dallas suburbs, they built 4,000 houses a year. I mean, it's phenomenal. And you can actually tell, these start at 100,000. These next ones start at 150,000. The next one start at 300,000. The next one start at 1 million. And everything is stratified accordingly. So the stratification will give you incredibly high spatial autocorrelation of, say, occupation and income, household income, and so on, because that is how people sort themselves in these neighborhoods. In European cities or in Asian cities, this is not, much less the case. Okay? And in European cities, you can find very high-priced houses next to very low-priced houses, because history has been working and has been mixing things around in various ways. And then you have heterogeneity, you have differences. Things are different in different places. So we'll talk a little bit about this as we get to the local test of spatial autocorrelation, but not too much. This is mostly about, most of our examples will have to do with positive spatial autocorrelation and clustering. So the bottom line of all of this, and I think I've said it enough now, the fact that you find clustering or positive autocorrelation does not mean necessarily diffusion. And the same for negative spatial autocorrelation. It does not necessarily mean competition, although those are both very good candidates for the kind of process that might have given you this pattern. So now let's move on to the operational side. We've seen the concepts of spatial autocorrelation, what it really means, and then how it gets put into a statistical framework against the null of spatial randomness. Now we'll operationalize this and focus on two major aspects. And this is where I just reiterate, our focus will be primarily on positive spatial autocorrelation. Negative spatial autocorrelation also happens, but much less so in practice. And I just want to reiterate the distinction that we've made in the point pattern analysis, where we made a distinction, and you just went through this in your assignment, between clustering, which is a characteristic of the overall pattern, and clusters, which are locally specific, location-specific characteristics. So in the context of values now, what are we interested in? In clustering, we are interested in an overall pattern for the data, in a map, if you wish, of the values, where the like values are more grouped in space than they would be randomly. And so, in a nutshell, what we're going to do is come up with one single number to characterize this whole pattern. And so our spatial autocorrelation test statistic will be one number, and based on that number, we will reject the null hypothesis of spatial randomness. So it's very important to keep in mind, this is a characteristic of the whole map, of the whole pattern. So never reject the null of spatial randomness and then say, here's my cluster. Okay? And there's some classic examples of this in the literature. I don't know if I mentioned this, but there's some classic studies that deal with the stroke belt. In the US, there is a much higher incidence of stroke in parts of North and South Carolina and Georgia. And it's a phenomenon that's been going on for multiple decades. It's a mystery, basically. Is it genetic? Is it environmental? Is it behavioral? You know, which is it? And so the early studies that looked at spatial patterns in stroke rates looked at them at the state level. And they do a Moran's eye, which we'll see later is the most commonly used statistic for spatial autocorrelation. And they find positive spatial autocorrelation and conclude that this confirms that there is a stroke belt in the South. Now, if you take this data and you do a local analysis, then you find that, in fact, it's not the clustering of the high values in the South that drive this Moran's eye, but it's the clustering of the low values that are not in the South, in the upper Midwest and, Northwest. They're the low values for stroke, and they're actually the drivers of this positive spatial autocorrelation. So be very careful when you conclude positive spatial autocorrelation. It's about similar, and similar could be high or could be low. So finding a highly significant positive spatial autocorrelation coefficient does not necessarily mean that it's the high values that cluster. It could be that it's the low values that cluster, and that is driving the process. So it's very easy to fall into that trap. But as we move to the second aspect, which we call clusters, which are the local characteristics of the pattern. And so where are there similar values that are more grouped than they would be randomly? And this is very interesting, because you could have a situation where the overall pattern is spatially random, in that there isn't sufficient evidence, given the whole map, to reject spatial randomness. But there are selected subparts in the map that are not behaving as they should spatially randomly. So those are local characteristics. And these local characteristics can go hand in hand with global autocorrelation, but they don't have to. And this is the interesting aspect when we move to local spatial autocorrelation. You can actually identify where the clusters are or where the spatial outliers are. And with the particular test statistic that we will look at, we will be able to actually distinguish between clusters of high values, clusters of low values, spatial outliers where highs are surrounded by lows, and spatial outliers where lows are surrounded by highs. And that's where we will end this analysis. But before we do that, what I'll do the remainder today is just give you a kind of at a conceptual level what a test for spatial autocorrelation is, and then spend some time on spatial weights. And so what is really a spatial autocorrelation statistic? It's a number. A statistic is a summary of the data, just like an average or a mean. You compute it from the data. So we need to come up with something that we can compute from the data, and that will tell us whether this particular map, this particular pattern, is spatially random or not. And the way we do this is we combine two aspects. We combine, it's all about similarity. Right? We combine similarity in value and similarity in location. So basically what we're trying to do is come up with some kind of mathematical formulation that summarizes the data and that combines the characteristic having to do, what we're interested in is finding whether like values are near each other. So we need to come up with something that formalizes what is like values and that formalizes what is near each other. So they combine the notion of what I call value or attribute similarity and locational similarity. And then we have our data, and we compute this number. Let's say we come up with a new autocorrelation statistic, which is the difference between the most east location and the most west location. Now, of course, it doesn't make any sense, but this is an example. And it formalizes locational similarity, and it formalizes attribute similarity. So we get a number, and then we have to figure out what does this number mean. In other words, how likely is it that we would find this particular number in a spatially random data set? And then if we conclude that this is not likely, or I should say not likely enough, then we reject the null hypothesis. And so let's say we have a number, 50. And we find out that under spatial randomness, the probability of getting a 50 is 1 in 3. Would we reject a null hypothesis? Most people would not. But if we get the result, say that getting a 50 is 1 in 1,000, then we would reject a null hypothesis and reject spatial randomness. So there's really three things involved here. Formalizing attribute similarity, formalizing spatial or locational similarity, and then finding out what is the distribution of this statistic, of this particular formula, under the null of spatial randomness. Those are the three pieces. And with those three pieces in hand, we can carry out statistical inference. How do we formally express attribute similarity? So this is some kind of summary of the similarity or dissimilarity of a variable at different locations. Remember, it's autocorrelation, so it's the same variable. How can we formalize whether the crime in two neighborhoods is somehow similar or dissimilar? Well, dissimilar is easy. We take the difference. And to get rid of sign effects, we square it or we take the absolute value. Similar is maybe a little less intuitive, but just think of a standard correlation coefficient. It's called a Pearson cross-product correlation coefficient, because the product gives us information about similarity. And think of it first in terms of just the usual correlation. If things are not correlated, then if you match them, there shouldn't be any systematic matching of highs with highs or lows with lows. So the product of these two values would be some kind of mix, some random mix of matching. But if there is structure so that the highs are always together, then you get a lot of really big products of these highs multiplied together. And also a lot of really small ones, of the small ones multiplied together. And that is more systematic than it would be random. So we're looking at something similar here, where we will take the product of the two values and then see how that relates to the locational similarity. So there are three main, there's others, but the three main measures of attribute similarity are the cross product, which relates directly to the notion of a covariance, the square difference, which relates directly to this notion of the semi-variogram that we had previously, and then the absolute difference, which is sometimes used to do robust estimates of a semi-variogram, but it's not quite the same. So one is similarity, the cross product. Two are dissimilarity, square difference, and absolute difference. And then the tricky one is locational similarity. How do we formalize that? How do we formalize the notion of neighbors? And we do that by means of these spatial weights. And they're just a mathematical tool to formally express whether I and J are neighbors or not. And I purposely put this as vague as I do, because it is really very general. Most of our applications, neighbors will mean geographically next to each other, contiguous, because that's easy to do and you have the GIS to do it for you. But it doesn't have to be. It could be neighbors in a social network, who you interact with. If you're looking, say, at voting results, is your voting influenced by the person who lives next door or by the person you happen to talk to at work? That is a spatial neighbor concept versus a social network neighbor concept. And there's some interesting work along these lines dealing with gang behavior. You know, are gangs social networks or are they spatial networks, and that they're associated with particular streets or street corners or sides of streets versus, you know, people who connect in various ways and form a social network. So there's also a notion of economic neighbors, social neighbors. It's very general. And in one of the readings, I just put it there for your information because it's like 40 pages. But there is a review of non-geographic notions, general notions of spatial weights, and there's a lot of them.